All right, so we're continuing with section 4.3, the Riemann sums and definite intervals. The next page in the notes deals with the variable of integration. Is often called a dummy variable because it can be replaced by any other variable without changing its value. So, in other words, we can think of something like the integral from 0 to 3 of the function x plus 2 dx. So we're considering sort of the regular y equals f of x kind of deal. That is the same thing as if I found the integral from 0 to 3 of t plus 2 dt. Those are actually the same thing. So that variable is called a dummy variable because it could be anything. It could be in that place, it could be a z or a j or whatever letter you want it to be. Now, one thing that we want to talk about is when we have a definite integral from a to b, f of x dx, the implication is that a is smaller than b. Okay, a is to the left and b is to the right. So those are values of x equals a and x equals b, and a is generally the one on the left side. But what if we had a situation where they gave us a definite integral where a were equal to b? Or what if a were greater than b? What would we do? Well, these definitions are going to be expanded so that a does not have to be smaller than b. So let's start with a equals b. What if, for example, I had a function and I wanted to find the integral from 3 to 3 of f of x dx, where a and b are the same. So I'd go to 3 and stay there, not move. And how much area is that? Well, the width from 3 to 3 is 0. So we'd have a width of 0 times the height of f of 3. That 0 is for width. The width is 0. And of course, 0 times that function output is 0. So anytime a and b are the same thing, no matter what the function is, the integral from a to a of f of x dx is always 0. Then the next thing I want to talk about is, well, what if I had an integral where here's a function and the definite integral states that I'm going from b to a. In other words, b is smaller than a. Oops, I wrote that wrong. Take that back. This would be the integral from b to a. Oh, I'm sorry. I need to put in actual numbers for this to make enough sense for it to be valid. So let me just change that. I'm sorry. Let's make this 2 and this 7. This is our f function. And someone asks you to find the integral from 7 to 2 of f of x dx. Well, if I were to think about our representative rectangle, if we're moving from 7 to 2, that's movement from right to left. And that would make our delta x, in this case, moving from right to left, a negative number. Okay, moving from right to left, that would make delta x a negative number. And if f of c sub I is positive, then the product will be a negative value. So you'll be adding up in this particular picture a bunch of negative values of these rectangular areas, so to speak. And of course, the sum of a bunch of negative numbers will be negative. And as it turns out, which is really kind of handy, if we were to have found instead the integral from 2 to 7 of the same function, that would give us that positive answer that is the area. And the answer we're going to get is really the opposite of that. So you can switch the bounds of the integral if you multiply by -1. Okay, so that leads us to the properties of definite integrals. The definitions of two special definite integrals is, if f is defined at x equals a, then the integral from a to a is equal to 0. That's what we just talked about right here. Then if f is integrable on the interval from a to b, then the integral from a to b, like 7 to 2, the integral from b to a of f of x dx would be the opposite of the integral from a to b of f of x dx. So those are really nice properties to help us evaluate integrals. All right, so do a couple of examples here. What is the integral from pi to pi of some function like sine of x dx? Well, since those are equal bounds, we're going from pi to pi, same number. That answer is 0. Okay. Next one asks us to find the integral from 3 to 0 of x plus 2 dx. The lower bound is smaller than the upper bound, and so I'm going to use that second property and rewrite this in a order that makes me happier. Go from 0 to 3, x plus 2 dx. And in order to make that change, I had to put a negative sign out in front of the integral. And if you look back at prior problems that we did, we had done the integral from 0 to 3 already in a prior example. And so all we have to do is just say, what's the opposite of that answer we got earlier? That's going to be negative 21 over 2. So I kind of cheated a bit there. I intentionally used one where I already knew the answer. So I could just take the opposite of that answer and get the final answer for the integral from 3 to 0, which is a pretty nice couple of properties to know. Now, next property I'd like to talk about is this one. If I have a region under f, and I am making it non-negative just to make it easier to think about, and I'm going from a to b, and there's some number between a and b, c, that I'm interested in using. Well, would it make sense to say that the total area from a to b of f of x dx, couldn't I say that that's going to be the area from a to c of f of x dx, which is this part of it right here, plus the integral from c to b of f of x dx? Doesn't that make sense geometrically? So that first area that's already shaded plus this area shaded the other way, those two areas would add together to be the total area. And this may seem like, well, why would you even want to do that? Why don't you just go from a to b? There can be problems where we need to stop at a certain point at c and figure out what it is from a to c, because we know how to do that. And then from c to b, it'll be a totally different kind of problem, perhaps. And we'll need to then integrate from C to B and add the two results. At first, this may seem like, oh my gosh, why were we doing this? It will become clear as we go that that's actually a thing that we need to be able to do. So, for example, to make that clear, if I were to ask you to integrate from -1 to 1 the absolute value of x dx, I know that I can't integrate, let me put it this way, I don't want my function there to be an absolute value function. That's not a good thing. So I'm going to use the definition of absolute value, which says that the absolute value of something is that something as long as that something is greater than or equal to 0. And when x is less than 0, we'll have to take the opposite of that something to turn it into the positive answer. So, and if we look at the graph of that function, of course we know it's this v-looking thing. What we're going to do is we're going to go from -1 to 0, and then from 0 to 1. So to get rid of the absolute value, and this is one of the reasons why you might need to split into two separate things, is we're going to go from -1 to 1, and to 0. And for that part of the curve, or it's not a curve, that part of the graph, the function is expressed as opposite of x. And then we're going to add from 0 to 1, and the expression of that function from 0 to 1 is just x dx. And then, of course, we have two triangles. So the absolute value of -1 is 1, the absolute value of 1 is 1. So those are the heights of our two triangles. So 1/2 base times height, 1/2 of 1 times 1 is 1/2, plus the other triangle, 1/2 base times height, 1/2 times 1 times 1 is another 1/2, which makes our answer 1. Okay. Now, a couple of other properties on the next page. Theorem 4.7 is that if you have the definite integral of k times f of x dx, that k can be pulled out in front. That should sound familiar. And number 2, the sum or difference of two functions as the integrand can be split up into two integrals. So the integral of f of x plus or minus g of x dx from a to b will be the integral of f of x from a to b dx plus or minus the integral of g of x from a to b dx. And of course, if you have 4, 5, 7 functions that are added or subtracted, you can just basically think of distributing that integral to each term of that problem. So, for example, we're asked to evaluate the integral from 1 to 3 of the opposite of x squared plus 4x minus 3 dx. Given that the integral from 1 to 3 of x squared is 26/3, given that the integral from 1 to 3 of x, oops, I forgot to write the dx before. Wow, I need to fix that. Please don't forget to write the dx. That's actually part of the symbols that you need to keep. It's important. It's representing that width, delta x, and so it has to be in there. So please, please, please don't just accidentally drop it. It's part of it. It's like the right parenthesis has to be written when you have a left parenthesis. When you have an integral sign, you have to have a differential, dx or dut or whatever the variable happens to be. Okay, so the integral from 1 to 3 of x dx is 4. And given that the integral from 1 to 3 of dx, so that implication there is it's 1 dx, that integral is 2. All right, so I've given you all those. And sometimes this is the way the problem will be stated to see if you know the properties or not. So what you're going to have to do is employing the property where the sums and differences can be split up into various integrals. This will be the integral of the opposite of x squared dx from 1 to 3, plus the integral from 1 to 3 of 4x dx, minus the integral from 1 to 3 of 3 dx. Then we can use the property of any constant multiplier. K can be brought out. We're going to bring out that negative sign on the first integral. Bring out the 4 in the second integral. And bring out the 3 in the third integral. Now we have expressions that involve our givens, so we can substitute for the first integral with 26 thirds, so it'll be the opposite of 26 thirds, because that was given, plus 4 times, then that integral from 1 to 3 of x we were told that it was equal to 4, and minus 3 times, and we were told the integral from 1 to 3 of dx is 2. And then it's just arithmetic. Okay, so do that arithmetic and you should get 4 thirds. Okay. Some more properties of integrals. If you have a function, say this one is g of x, and this one is f of x, and we're going from x equals a to x equals b. If f and g are both continuous on a closed interval from a to b, and from a to b it's clear that this statement is true, that 0 is less than or equal to all function outputs, so f of x is non-negative and non-zero, or no, it can be 0, my bad, which is less than or equal to g of x. So f of x is lower than g of x, and the x-axis is lower than f of x, is what that means. If all of that's true, and by the way, if a is less than or equal to all the x's, which is less than b, if those two statements are true, along with the continuity statement, then what we can conclude is that the area from a to b under f of x, which will be represented with this definite integral, compared to the definite integral from a to b of g of x dx. Well, since g of x is higher, the area under it has to be greater than the area under f of x, and so that inequality would always be true given those initial conditions. So in theorem 4.8, if f of x is non-negative, then the integral from a to b of f of x dx will never be negative. It'll always be 0 or bigger. And if f and g have the kind of relationship we just described, for every x in the interval, then the integral from a to b of f of x dx will be less than or equal to the integral of a to b of g of x dx. All right, that ends this session. I'll see you later.